In this lesson, we're going to take a look at the ratio of areas of similar figures. Let's begin by getting two similar triangles. So here I've constructed a triangle, and I'm going to make a second triangle that is going to be twice as large in terms of the lengths of the corresponding sides. So here's my triangle, and this is my center of dilation. I'm going to use a scale factor of 2. So this triangle, all the corresponding sides are twice as long as the original triangle. And down here, notice it automatically calculated the area for us. Let's take a look at the ratio of the areas. I'm going to take the area of the bigger polygon, so that would be polygon 1 prime, and divide it by the area of the smaller polygon, polygon 1. And notice here I've got an answer of 4. Even if I drag on this triangle here and make the sides longer or shorter, the ratio for the scale factor is 1 to 2, but the ratio of the areas is 1 to 4. In other words, it would take 4 of these triangles to fill up the same amount of space as this triangle. Let's see, does that make sense? Well, the base is twice as long and the height is twice as high. And to find area, we would take 1/2 base times height. So I'm doubled the base, I've doubled the height. That means the area that we need to fill this triangle would be 4 times the area for this triangle. What about the perimeters? How do the perimeters compare? Well, let's add the sides of the one triangle together, the smaller triangle. So this is the sum of the sides, or the perimeter for the smaller triangle. Let's do that for the larger triangle. And here it doesn't look like the ratio is 1 to 4. It looks like the ratio is 1 to 2. Just like what we'd expect, since the ratio of the corresponding sides is 1 to 2, the ratio of the perimeters would be 1 to 2. What do you think would happen if, instead of a scale factor of 2, which gave us a ratio of areas of 1 to 4, we use a scale factor of 3? Let's investigate that. And this time, let's actually use a slightly odder shaped polygon. Let's make this one really, really strange here. And let's create a dilation where we're going to have a scale factor of 3. So this is 3 times bigger. And whoa, look at how much bigger the area is. Let's take a look at the ratio of the areas. Let's take the area of polygon 1 prime and divide it by the area of polygon 1. 9. Interesting. So that means that it would actually take 9 of these shapes to fill up the same area as this one. And the scale factor was 1 to 3, but the ratio of the areas is 1 to 9. Interesting. Well, let's take a look at our handout of notes and see if we can figure this out. If two figures are similar and they have a scale factor of A to B, then what's the ratio of the perimeters? Well, the ratio of the perimeters would be the same as the scale factor. The ratio of the areas, however, is A squared to B squared. Now I know the examples that we looked at were a ratio of 1 to 2, and we saw that the ratio of the areas was 1 to 4, and then we had one where the ratio for the scale factor was 1 to 3, and the ratio of the areas was 1 to 9. But if we had two figures whose scale factor was, let's say, 2 to 5, that means the ratio of their areas would be 4 to 25. It's the scale factor squared. Let's take a look at the next problem. For this example, it says that D, E, and F are the midpoints of the sides of triangle PQR. So let's create a triangle here. And it says D, E, and F are the midpoints of the sides of this triangle. Now we know from a previous chapter that when we connect the midpoints of two sides of a triangle, it's parallel to the third side. And we also know from that same unit that the length is half as long. So let's label these segments. So D, E, and F are the midpoints. So I'm marking off the segments that are congruent. And then the original triangle is PQR. So the scale factor is 1 to 2. Because if you think about it, we've got similar triangles here. And we know that DE is half as long as PQ, and RE is half of RQ, and RD is half of RP. So we know that the scale factor is 1 to 2. The ratio of the perimeters is also 1 to 2. So this is our scale factor, and this is our ratio of our perimeters. And then we know from the theorem that we just got done looking at that the ratio of the areas is a scale factor squared. So this will be the ratio of the areas, 1 to 4. And if you think about it, that makes sense because there would be 4 triangles like this one. Like this one here. There's 2. Here's 3. And then here's 4. I can get it to rotate in there. There we go. So there's 4 triangles of equal area filling that up. Let's take a look at the second example. In this example, we're told that the area of a quadrilateral is 57 square centimeters and its sides are 7, 8, 6, and 4. I'm just going to draw some kind of quadrilateral here. It doesn't really matter exactly what it looks like. It's not a very good drawing, but you get the idea. This will say is 8, this will say is 7, this will be 6, and this will say is 4. Imagine those sides are straight. All right, its area is 56. And it says find the area of a similar quadrilateral whose should be neither longest side is 12 centimeters. Well, the longest side of a similar figure would have to correspond to the longest side of this figure. And the longest side of this figure is 8. So we would compare 8 with 12, and if we reduce that, we would get 2 to 3 for the scale factor, which means the ratio of the areas is the square of that, and that'd be 4 to 9. So we need to compare short side or smaller figure to larger figure as we set up our ratio, and the area of the smaller figure is 56. So when we solve this proportion, we would end up with x equals 126 square centimeters. Don't forget to do the survey at tinyurl.